is going to be titled as partial DG category and mixed motives over K bracket T over T with power m+1. And probably maybe many people might be wondering what kind of title this is and maybe have no idea what it is about. But this is supposed to be a very elementary talk, and I will just tell some very well-known formalism actually. So those who are working on some remote fields such as homological mirror symmetry will probably recognize that this formalism is actually introduced over here. So I'm working on motives, but this formalism was actually used by Japanese mathematician Masaki Hanamura when he constructed triangulated category of mixed motives around 1996. It was published in Invention around 2004, but the method hasn't been generally much well known to algebraic geometers, but homological mirror symmetry people actually use it all the time, although there was some minor errors, and people just copy the error repeatedly many times, so I will probably mention where the errors occur. So let me give you an idea about what is, first of all, the DG category is, because this is going to be kind of general talk for people who are not actually studying this kind of subject. Maybe it's better to talk about this. And I will actually emphasize that this is, sometimes people want to say pre-additive, but pre-additive means that direct sum of objects may not be really in the category. But so I will tell you what DG category is. What is DG category? It's a category, but with some special property. So DG here means differential graded. So there should be some kind of homological algebra going. So the idea of DG category is going to be this. So we have a category C, but one requirement we suppose is that, okay, suppose that this DG category is over a commutative ring with unity R. So in case you take R to be a field, that's going to be actually complex of some vector spaces. But anyways, it just works for arbitrary commutative ring with unity. C is a category, and of course for each object, we don't really do anything. We suppose that there is an object. But for DG category, we actually do something for the morphisms. So suppose we have actually two objects, A and A prime. Then for a category to be DG, differential graded, what we require is that we have this home from A to A prime, and we want this guy to be a complex. So some people don't really like this notation, but this com-R means this is going to be the category of complexes of R modules. So this is complexes of R modules. So here we actually have natural differential because this home is going to be actually looking like this. We have home n AA prime that goes into home degree n+1 A and A prime, and we have something else here, home n-1 A and A prime, and at each step we have differential. This is going to be complex. So DG category is actually a category where morphisms are actually complexes of R modules. So because complexes are differential graded, this is why we call it DG category. Okay, so we have a DG category, and we might probably want to know, of course this is not the only requirement. Of course we need some kind of compatibility. One extra compatibility condition, of course, that we need is going to be, of course, associativity of compositions, and also Leibniz rule, as most of the differentials must satisfy. But another thing is going to be some kind of identity rule. So for each object A, we have, so this, oh, it's okay, not Z, but we can take R. So R is the commutative ring with unity, and this is regarded as the unity for the category com R, and we have the identity morphism from home A, R to home A. So this A and that A are same. And here I send 1 to the identity. And we require that this is going to be degree 0 map. And this identity map should actually satisfy the left identity axiom and right identity axiom that are actually fairly obvious. So I wouldn't probably bother to say too many things about this. So, but the key point is the differential graded algebra is so differential graded category is a category where the morphisms are actually differential graded. Okay, so let me give you some examples of these. And actually this is appearing in most of the subjects of mathematics that I'm aware of. So for instance, suppose for simplicity, R is the ring of integers. And maybe you can say, first of all, this COM-Z, the category of complexes. This is itself actually, is itself a DG category. So one of the most common way of giving this kind of DG structure for here, suppose I have this A and B, then we need to define actually home in this category, AB. AB are already complexes. So what we can actually do is, well, there is actually some kind of complicated notation. If you look at any of the homological algebra books, generally many people actually like to look at the books by maybe Gelfand and Manin and various people. And they generally use this kind of notation where this is actually a complex where home N, A, B is defined to be the product over all grades I of home. And we have from AI to BI plus N. So basically degree N element for this is going to be something that increases the degree of the morphism here. So that's going to be actually making a DG structure. This is actually purely coming from general homological algebra. It's actually a very basic kind of thing. And you can define the differential capital D over here by simply requiring the Leibniz rule. But from geometry, you can also have a lot of things. Suppose X is a C infinity manifold. And suppose that V is, say, okay, so before I say, suppose I want to define some category which is DG. So C is a category where objects of C are going to be actually flat bundles on X. So X is fixed. And what is flat bundle? So this is going to be, i.e., C infinity vector bundle, say V on X, equipped with a connection, equipped with a connection. So connection is a way of differentiating vector sections of vector bundles, connections delta. So here I have AX0 is smooth functions, tensor over the structure shape of X, and we have V, and then we go to actually one forms, and that's going to be connection if the flat if delta squared is 0. So that's the definition of a flat connection. We can always define connections, but it's not always flat. Sometimes people call it integrable connection, depending on preference. But anyway, that's the same thing. So we collect all of the vector bundles equipped with the flat connections, and then what can you do with this? We can define morphisms and in the most obvious way, and that's going to be actually forming a DG category, actually pre-additive DG category, which is also additive. So how do we define morphisms? For vector bundles, it's very obvious. So as long as you have the notion of dual and tensor product of objects, it's actually very, very easy. So morphisms of C. Suppose I have two vector bundles with flat connections, V and W. They are C infinity vector bundles on X and with flat connections. And we can define home VW in this category C to be what? So this is going to be the RAM complex on X. So this is a complex of the RAM differentials, and we tensor it over the C infinity structure shift, and then we can take the internal home VW. So this is going to be another vector bundle, which is generally written also as V upper star with tensor with the W. So that's going to be also a vector bundle, and equipped with actually this one is also flat with a different kind of connection. And this is a complex. It's a RAM complex. You tensor with that vector bundle with a flat connection. So this is going to be actually a complex. So this is giving us a different kind of DG category coming from geometry. If you work with a complex manifold, then you can actually work with actually holomorphic differential forms and then use the Dolbeault complex instead. And that's going to be giving us also a different kind of DG category. So it's actually everywhere. A different kind of application that people can find is going to be many places in like homological, homological mirror symmetry people. I don't really know anything about this. I was told a rumor that there's an expert over there who is going to be giving some talk about what that is. And that's actually where this is heavily used. DG is actually very much used. So we can probably leave this subject to him. And so I will probably then, what am I going to be talking about? So here I gave you several examples and definitions of DG category. And I want to actually tell you one very, very well-known formalism. And I'm not actually going to be presenting that one only. I will actually talk about one modification of that well-known formalism, because I'm an algebraic geometer who need to work with algebraic cycles, and that's generally not suitable for that. Where do you use the connection? Here. Connection, where do I use the connection? Without having connection, this is not going to be complex. You need a flatness to have this connection. Unless the connection is a flat, tensor product doesn't give you complex. So we definitely need a flatness. Okay, so so the second section is going to do this. What do we do with this? What do we do with DG categories? Actually, this is actually a very stupid question because there are too many things we can do. So I will just tell you only one thing, which is the main topic of this talk. So I will present one thing which is actually quite well known, probably much older than the published result. So this formalism was actually originating from some people who were studying Hodge theory, but it was formalized by Bondar and Kapranov. And it was probably, I guess, in Kapranov's paper in 1988 or something, it has appeared, but Bondar actually used that one to prove something else. It was the paper that I'm talking about is going to be 1989 paper published in Mathematics of USSR Svornik, and there you can find something called. It's a little bit funny because and if you go to Math Science, it says framed triangulated categories, but actually the English translation is having title enhanced triangulated categories. So it's actually difficult to find the paper because of that mismatch. But the paper does exist uniquely, so it's not causing confusion. So you can probably find framed or enhanced triangulated categories. And you actually see that, although it sounds very horrible, because most people hate the triangulated categories, but this is actually quite a simple formalism. So what does this one do? The idea is going to be summarized in the following diagram. There were some minor inaccuracies that were ignored by most people, although it's not a serious flaw, but it's actually still a very good formalism. So suppose that we have a C which is a DG, actually pre-additive. Pre-additive means, again I say, the finite direct sum is not necessarily in the category, DG category. And out of that, because we may not actually have a finite direct sum, we extend this one to something that we call C+. So this is going to be really DG category, which is closed under finite direct sums. And then we define another DG category. This is actually the most complicated process, and this is the heart of the construction that people call pre-TR. And there, actually, Bondar and Kapranov defines for the first time what is called the pre-triangulated category. That has been actually very, very useful in various subjects. And then, out of this, people actually define the 0th degree cohomology category that people call TRC. And that's actually not a DG category, but it is something that is generally called the triangulated category. So what is triangulated category? It's very difficult to explain what is actually all this thing about. But the basic idea behind triangulated category is that suppose you do some homological algebra. To do some homological algebra, basically what you need generally is a Abelian category with injective objects, enough injective objects. And then you can take injective resolution and do all kinds of homological algebra. But the thing is, if you look at the axioms carefully, what you actually need is the derived category of the Abelian category, which is actually, roughly speaking, the complex of objects quotient out by quasi-isomorphisms of complexes. That requires some discussion, but a very fascinating property of that is that actually satisfies a certain list of axioms, such as the existence of cone and various other properties, and that actually forms actually triangular category. So derived category is a very complicated object. The triangular category is some kind of concept that sort of axiomatizes the most essential properties of derived categories of Abelian groups. And then basically the idea is that if you have a triangulated category, then you can do almost all homological algebra you want. As long as you have a triangulated category, you can do homological algebra. So for instance, derived category allows you to do that. So of course, DG categories allow you to do the homological algebra, but this is actually much better. So anyways, this is actually formalism. Of course, the paper is not really, main point isn't this. Actually, they proved a different kind of theorem about finite generation result, about triangular categories. So this is actually part of the construction, but this is so useful that it has been adapted by so many people. So let me explain what all of these things are. So there are actually several steps. Number 1 and 2 and 3. And 1 and 3 are very simple. 2 is quite complicated. So what is number 1? The first step is fairly simple step. Suppose you have a category and the category doesn't have finite direct sum. Direct sum is generally called the coproduct. What do? Well, you can just artificially increase the category by throwing in objects. So suppose I have, say, x and y in the category, and we know what it means to say homes between these in this category. But because we don't really have direct sum, x direct sum y doesn't really make much sense. So suppose I have actually these guys. Then we just artificially create the category C+, where the objects are precisely finite direct sums of certain objects on C. So that's actually very easy. But what about the morphisms? For morphism, there is an obvious way to do. So if I have xi with a parameter I and yj maybe with a parameter j, then what is going to be home between the direct sum of xi's and direct sum of yj's? Well, that's going to be just obviously, you can define it as direct sum over two different indices I and j, and then you can take the home xi, yj. So in this way, you can actually extend this one from here to here all the time. This is closed under finite direct sum. So this is, in a sense, completion against the taking finite coproduct. So that's actually a fairly easy process. This is actually a very, very, very difficult subject. So this requires some thinking, and it's not going to be very simple. It's actually generally taking very long time to understand what's really behind this. So let me explain this number 2. So what is this? So here I have to assign a different kind of DG category out of these guys. So we define one concept, which is the definition was actually given by Bondar and Kapranov. Actually, Kapranov might have given this terminology. And so what is this? So let me give you a definition. So suppose D is one DG category. So here our D is going to be C+, and then a twisted complex over D is a system. We are going to be defining an object in this category. It's a system, but in this system, it actually contains finitely many objects in this category. So this is actually indexed. So we have objects where the first component is the collection of objects indexed by Z. So AIs are objects in the category D. But we actually join certain other things that we call QIJ from AI to AJ. This is a morphism in D, with the requirement that, first of all, we have actually, so this Z has infinitely many indices, but we don't want to have actually infinitely many objects. So we require that AI is 0 for all but finitely many. So that's actually just fine. But the second requirement that we want is that this QIJ is going to be a morphism. So here, recall that this D is a DG category, so that all of the morphisms are actually elements in the complex. So we have to specify where this guy lies. And we actually require the degree of this morphism QIJ is actually I minus J plus 1. So that's the second requirement. But that's actually not all of them. So we have actually one more axiom. One more axiom that we actually require is looking very bizarre to most people. This is actually where the first minor error of Bondar-Kapranov actually appears. So what is that? So the third condition is we put this differential dqij and put minus 1 into j, certain sign over here, and then we take the sum over all possible indices L of qil composed with the qlj. So keep in mind that qij is a morphism from AI to AJ. What is this? The right-hand side sum is we are taking the sum over all possible passes. So you have AI plus 1, AI plus 2, suppose say maybe AI plus 3. And for each of these, you have various maps. So this is going to be QI plus 1, QI plus 1, QI plus 2. We have this one too. But also, we have map over here too. We have map over here too. We have map over here too. And we also have, okay, so this is actually a picture of all possible compositions. And because we are not requiring really anything, what actually happens is that from this object to that object, there are actually many, many different ways to go. So this actual condition is saying that, okay, we can probably take a sum of all possible ways from AI to AJ, and we require that thing to be actually trivial after taking homology. One thing that I have to remark is that in the original paper by Bondar and Kapranov, this sign is missing, and without this sign, it's not going to be working. So I will just put this sign over here because it's going to be the right correction to do. But basic philosophy is that this is going to be saying it's kind of, so regardless of what kind of passage you take, this is going to be killed by after taking homology. So in other words, or if this is actually, there are too many things, it's very confusing. If you think about 3 things, then what it says is up to a sign, going this way is essentially the same as going this and that. Okay. So we require that, and this is called a twisted complex. So that's going to be actually basically the collection of objects of this pre-TR. So pre-TR consists of objects that are exactly twisted complexes of C+. So objects of pre-TR C is basically the collection of all twisted complexes over this C+. So that is actually a very nice one. But the problem is that now we have to define the morphisms. So the objects of this triangle this category is already objects from the previous one and the morphisms. Now the morphisms, suppose I have A is AI and QIJ. So let me call it PIJ. PIJ. And B is BI QIJ. Then what do we do with this? So we have to define morphisms. So home from A to B, where I have to emphasize that this is the morphism in pre-TR. And we want this guy to be a DG category again. So this guy have to be a complex but the definition of this one is actually one thing that makes people suffer really a lot. So by any chance, if you go back and try to look at the paper, then it takes several days maybe to see why he is doing this. So probably home, so where home K of pre-TR of AB is defined as the direct sum of the previous elements of the complex parts of complexes home L with C plus of AI Bj. So A and B have a lot of objects in there already. So this is in the category C plus the degree L component of the complex from AI to Bj. And the index here is like this. We take the sum over all possible indices where K is fixed, but the sum is ruled by this. L plus J minus I is equal to K. There is actually, it looks very random, but if you think about it for a while, you realize that this is the way it should be. And then, so this one is just still the direct sum of objects. So we have to define now the complex, actually differential. So here the differential is not definitely going to be the usual differential over here. So here the differential was small d. But now I have to define the differential for this home for the pre-TR. So let me call it d. So d is the differential. And I have to recycle the differential for that one. And this is where some of the worst kind of calculation comes in. So if I have an element f here, then I define this differential to be minus 1 with j and df plus sum of all possible indices m of certain sign minus 1 j plus m qjm composed with f plus. You don't have to remember this kind of thing. It's a nightmare actually to remember this. Okay, so let me write it. Plus minus 1 with the sign L plus J plus M plus 1 and F composed with the P MI. Yeah? Yeah. Yeah. Yeah, yeah. 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 You have this complex, so this DG category with a differential small d. Now I need to define the capital D, which is differential for this morphism of pre-TR. And you probably realize this is really horrible looking formula. And actually the thing is, in the original paper by Bondar and Kapranov, these signs are missing, and this sign is not correct. So that if you try to prove d squared is 0, then you are not going to be able to verify that it's actually not working. So we spent a lot of days to figure out what the correct signs are. And it's surprising that actually many of the papers that I have been looking at through in mostly homological mirror symmetry subject, because this is actually used most often there. And all of the people I have seen were using exactly the wrong signs. So it's pretty surprising that for 20 years, nobody has bothered to correct these signs. Nobody calculated this one until I did it with my collaborator a few weeks ago. But anyway, this is the correct sign. So if you just don't want to remember, you can probably look at my recent paper. This is the place where we actually give the right formula for the differential. And we also contain this proof that d squared is 0, because not at all this one was written anywhere. So, but I think anyway, the idea of Bondar and Kaplanov was precise, that everything was working up to sign, and that itself is actually very surprising, because people cannot really come up with this kind of thing. But it still looks very messy, and people don't generally have much intuition about why people define things in this way. So that's actually one problem. But what is actually amazing is, this actually does very good job. And furthermore, what we can prove is, it actually has some kind of structure of various structures actually. Especially, okay, forget about all other structures. Just take it as a differential graded category. Then for each differential graded category, we can associate its cohomology. Objects will be the same, but for each morphism, we can simply take the zeroth cohomology. They will give us a morphism. And then this is actually TR of C. And then the rest is going to be working fine. So what actually Bondar and Kaplanov did is, they proved that this is a triangular category with a natural shift structure and the natural cone structure. They declared what distinguished triangles are. But this is actually something that looks very bizarre. So maybe I need some kind of more explanation about that stuff. So that's actually where certain problems that came in. So, and that problem is actually appearing in a funny way when I was trying to generalize this formalism of Bondar-Kaplanov to something a little bit weaker. So let me just erase these things, and let me just tell you what precisely was going on, especially regarding this formula. So when I was trying to generalize this one to something that has a weaker property that we call, so this is section 3. We are working on something called the partial DG category. So partial DG category is not a category actually. It's almost DG category, but it is lacking some properties, such as we cannot compose elements very well. If composable, it is associative, and we have a Leibniz rule. But one lacking property is that if you have two morphisms, for instance, home AB and home BC, they are all complexes, and generally we want, by composition, we want an element over here. But the trouble is, the composition rule will not necessarily be defined everywhere. What happens is, this actually really happens in subjects like algebraic cycles, because in algebraic cycles, those kind of compositions generally coming out of intersecting cycles. The trouble is, algebraic cycles is actually too much. There are too many things, so that if you try to intersect them without actually moving this into proper position, this is not well defined. But moving is generally allowed up to certain quasi-isomorphism. So you actually have a quasi-isomorphic subcomplex, and on that quasi-isomorphic subcomplex, you can actually compose things. So the restriction here is that this composition is not defined everywhere. So that's actually one weakening of this DG concept. But another thing is, we actually rather have this is actually is defined. So for a fixed f, for instance, suppose f is fixed over here, then this composition is defined on some quasi-isomorphic subcomplex of this home AB. And the same thing is true for if f is over here on the right hand side, maybe let me call it G. And this is also defined on a quasi-isomorphic subcomplex of home BC. So actually, in the definition of DG, partial DG category, we actually give this. For each object A and B, first of all, we have this home AB, which is a complex, just like DG category. But we also associate a collection SAB of certain quasi-isomorphic subcomplexes. So this is a collection of quasi-isomorphic subcomplexes of this home AB. And that satisfies cofinality condition in that if I have one quasi-isomorphic subcomplex and another quasi-isomorphic subcomplex, there will be actually a smaller quasi-isomorphic subcomplex which is contained in both of them. So that condition is not actually obvious. It looks natural. If you take the intersection, that it seems it might be working, but actually if you try to write down the proof, you actually find some holes. So we require this one as an axiom, and also require this part that if you fix an element, then you can find a quasi-isomorphic distinguished subcomplex as also a part of axiom. So we require this and this, and that's actually what we call a partial DG category. And so over here, it was actually possible to prove that you can still define the twisted complex. You can do almost all of these, and we can actually prove the theorem that Bondar and Kapralov came up with about 20 years ago. So the theorem is, this actually was used first by Hanamura, but he didn't write things in this way. So we actually formalized this because we needed to use this one to different situation. So Hanamura, who constructed a category of motifs, and it was also done by my collaborator with myself. And so even though C is not a DG category, C is a partial DG category, still this TRC is a well-defined triangulated category. So it looks like everything is going fine, but actually there is one missing hole. One missing hole that really requires a serious consideration is that, so because in homological algebra, we actually identify anything up to after homology. If you are going to take in homology anyway, then something that is a given complex and the subcomplex that is quasi-isomorphic are identified all the time. So it seems like everything is working. What trouble here is that this homology H0 is not against the differential small d, but this is a differential, is a homology against the differential big D. So the issue that you have to resolve is, suppose that you have a complex like this, home BC, and it's D quasi-isomorphic, small d quasi-isomorphic subcomplex. Then will they give the same quasi-isomorphic complex with respect to this capital D? So that's actually a very non-trivial question. You have one subcomplex that is quasi-isomorphic with respect to small d, then will it still give you quasi-isomorphic subcomplex with respect to capital D? And actually, if you just mess around a little bit, you realize that it's not actually very, very easy problem to solve. So what we actually have to do is, you cannot really make it work on the level of complexes or bicomplexes. You actually have to go to homotopy category. And in the homotopy category, what we can do is that these maps, actually Pij's and Qij's, and there was one requirement that I very cleverly raised, which was a part of definition, actually induce a homotopy between between certain maps. And in the homotopy category, and then you can use spectral sequences to identify the d quasi-isomorphic, small d quasi-isomorphic things to these big d actually ones. And another one is using that kind of spectral sequence argument, the morphisms of pre-TR can be written in terms of double total complexes in the homotopy category. So this one, so here is not going to be given, but so almost everything is fine. Almost everything of Bondar and Kapranov works, except if I have home AB and I have home a quasi-isomorphic subcomplex prime where the differential is going to be D. Let me just write down differential here as a subscript. That it is not apparent that this implies this home pre-TR, there will be associated subset over here prime and this A, B pre-TR with the capital D's. So whether these guys are actually also quasi-isomorphic. This is quasi-isomorphic. So that part is not going to be very trivial. So the resolution is the main idea is that you can realize this all the time as something called the right total complex and the left total complex of what is called C complexes. This notation was actually invented by Hanamura, but when we were actually looking at his invention paper very carefully, there was a small gap. The gap was that this concept actually has some kind of duality. Here, he was very careful in checking signs, but he missed actually one part. His notation was actually something that corresponds to the left one, and we also have to invent these right C complexes to correct the correct sign. So what is a C complex? C complex is really almost double complex, but it's a double complex only in the homotopy category. So you have actually objects that look like this. We have A1, A2, A goes to A3. And so this is a complex. And generally, if you want to have a double complex, then you might have a complex that is going up as well. So say A11, A12. But the trouble is that in the definition of C complex, this composition of two things is not necessarily 0. But it is 0 only up to homotopy. And that actually happens in most of the situations, especially in this partial DG category situation. And so this is actually 0 up to homotopy. So once you have this kind of thing, then you can still define the total complex of this by taking the diagonalized sums. But your differential for this total complex is going to be a little bit complicated. You have to take advantage of all of the homotopies that you have. So you define this one, but there is so this is a left C complex. The right C complex will have exactly the same shape, but with a completely different signs. So that's why we need actually total R and total L. But because these guys are actually really double complex in the homotopy category of objects, this is going to descending to the homotopy category. We will actually have exactly this description. So this is actually what was not given in the Bondar-Kapranov formalism. Hanamura's discussion was a little bit missing because he didn't really tell the differences between these two, and the proof was having a little bit of a gap. But having this one in mind, what we can see immediately is that suppose I have this given complex, I replace this guy with a quasi-isomorphic subcomplex. everything is the same. Then we have actually MAP. MAP of quasi-isomorphisms, which is quasi-isomorphisms through horizontal directions. Then apply the spectral sequence calculations, then they will actually give an isomorphism everywhere. So this quasi-isomorphism with small d will immediately imply quasi-isomorphism up to capital D, which is not actually very trivial. It can be seen only after actually you see that this is double total complex of certain C complexes that we actually do. So that's actually one theorem that we found out. And it turns out that actually this kind of thing can be actually now used to prove various things, but it seems like I have only 3 minutes, so let me just state the theorem, another theorem that I tried to explain the meaning of the differential, but somehow I have only 3 minutes, so let me probably say only the situation where this one really applies. So number 4. So number 4 is going to be an application of this pre-TR business of a partial DG category. And so first of all, by doing this, we were able to completely rewrite the Hanamura's construction of triangulated category motifs. So Hanamura considered something that looks like a C. So C is going to be in the category where the objects are smooth projective varieties. So X is a smooth projective variety over perfect field, and you have integer R. And for morphisms, we associate very simple thing, although I'm not going to be giving the definition of this. So I have X, R, and Y, S. Then the home in this category, X, R, Y, S, is going to be what is called the higher Chow complex, so dimension of X minus R plus S of X cross Y and minus dot. So this is actually called higher Chow complex. R is just an arbitrary integer. It sort of corresponds to the codimensions of these cycles. So they give the information about codimension of cycles. This is a complex, and given this complex, what we can show is that Hanamura's this category is going to be partial DG category. It's not a DG category. It is a partial DG category. So all of the things that we discussed so far actually work. And then he defined his category of motifs. So Hanamura's definition of categories of motifs, DK, that he wrote, is just nothing but actually this TR of this C with something called the pseudo-abelianization. So people call it sometimes Karoubian envelope, but the pseudo-abelian envelope is, roughly speaking, just artificial process that adds all of the images of the projectors. So this is some kind of extension to make the category nicer. And there is a theorem by someone named Paul Balmer and Marco Schlichting. They prove that this process preserves the triangulated structure of any categories. So this actually makes this one a triangular category, even tensor category. So that's actually one simplification of Hanamura's work. He wrote a paper that is like 100 whatever page long in 3 volumes. And that can be simplified in a much better way. And so the theorem that we actually proved is going to be that we can actually extend this one to different categories. And that actually gives a flavor of where some of the deformation theory aspect kind of thing might be appearing in this motif world. So, okay, so here he defined this one as the triangulated category of mixed motifs. And it was very recently proven that this is actually anti-equivalent to the Voevodsky's category of geometric motifs. So this is by Bondarko, only 2009. So the theorem with Krishna, who is my collaborator, is that we can actually work with a different category now, because we have now formalism. C is our category. C is going to be the same object, so X and R. X is a smooth projective variety, and R is an integer. And you can actually take morphisms of X and R and Y and S to be not just this, the higher Chou complex, but higher Chou complex actually together with what is called this additive higher Chou complex that we were actually after. So we put both of them together, and so to make this, so to prove that the C is a partial DG category, we actually need one thing called the moving lemma. Moving lemma for TG. That was actually done by myself and the Krishna in 2009. So that is actually the most essential actually trick. The moving lemma for this one was known by Spencer blog about like 1996 or something, but it hasn't been known for this TZ. Then we can actually prove that this guy actually works for that. So we can actually define a new category, DKM, which actually contains Hanamura's category of motifs. But also we actually have a surjection over here too. So that we actually have some kind of categorical, like a square zero extension kind of thing. So this is the Hanamura's category. This is our category. And all of the morphisms here we have actually a square zero composition. So in a sense, this is some kind of trivial deformation of Hanamura's category of motifs. And this actually satisfies various properties that were conjectured by people like Goncharov and several people. There were certain missing conjectures that we were not able to prove. But the main essential point is that by simplifying and modifying the Bondar-Kapranov formalism and Hanamura's idea, we were able to simplify Hanamura's construction category of motifs, and we were able to do this one. So we are working on Voevodsky's category of motifs, and want to simplify his construction and identify this one with our category. So that's actually one thing that I was driving over time a little bit. I'm sorry that this is has gone too far. Okay.